Okay, this is the day 14 lesson, the lesson on thermal effects. We're going to talk about thermal strain now. So instead of strain that develops because of stress that's been put onto something, we can also have strain that develops because of thermal effects. So we're going to talk about that and give a couple of examples. I mean, one place where you see thermal strain being accounted for or accommodated is in bridge expansion joints. The point of these little teeth right in here is to allow the bridge to expand and contract, and still maintain contact with other parts of the bridge. The SR-71 Blackbird is kind of a famous example of thermal effects because this thing gets so hot it travels about Mach 3.5, or I should say when it used to fly. It traveled about Mach 3.5, and at that speed, the skin of this thing would get tremendously hot. And some of you may know that most aircraft have fuel tanks in their wings, and this particular aircraft got so hot that it would have to have really big expansion joints, essentially, which meant that when it was sitting on the ground and it was cool, and you would put fuel in it, the fuel would leak. So it would actually leak fuel on the ground until it got up to speed and had the fuselage heat up, and then all those expansion joints would close up. Anyway, really crazy, some crazy engineering in that plane. And I just think that the quote is funny. 80,000 feet and climbing is just crazy high for airplanes. At the time that the SR-71 was operating, it was actually faster than missiles, and actually higher than missiles. Missiles that were launched from the ground could not go Mach 3.5, and they couldn't get to 80,000 feet. So for a long time, it was just untouchable. Anyway, interesting plane. So let's go on to thermal strain. Thermal strain is basically strain just like we've been talking about, but it's due to a temperature change, where alpha is the coefficient of thermal expansion, right? And the total strain in some object is just the summation of strain due to applied loads, like this epsilon sigma, and strain due to temperature changes, like this epsilon t. So we could say sigma over E, or stress over elastic modulus, plus alpha times delta t. All right. What about shear strain? Well, for homogeneous isotropic materials, when they don't have restraints on them, they basically expand equally in all directions when they're heated up. So the shape of the body doesn't get affected. So since the shape doesn't change, the shear strain, there is no shear strain, there is no shear strain, basically, due to thermal effects. Now, what's homogeneous and isotropic materials? Homogeneous just means it's the same all the way through, like all the all the parts, all the molecules of the material are the same. And isotropic means it behaves the same in all directions. Most engineering materials are homogeneous and isotropic. Especially things like steel, aluminum. Those are homogeneous and isotropic, or isotropic. If we have something that is like carbon fiber, where we have fibers moving in a particular or fibers laid up in a certain direction, then we don't have isotropic material. But anyway, so most of the time we're dealing with these types of materials, and we don't have any shear strain due to thermal effects. So let's take a look at an example problem here. One example of a thermal effect would be a bar that is constrained, like between two walls like this. If this thing is heated up, it's going to expand, but the walls are going to keep it from expanding, so you're going to induce a stress, right? So the total displacement of this bar has to be zero because of the walls, right? But we know that we're going to have a this thing's going to want to have a displacement due to temperature, and it's going to the walls are going to exert a stress back on it. So we could say that the displacement due to T is going to be like a epsilon T thermal strain times L. There's also going to be a epsilon sigma times L. That's the strain due to a stress equals 0. All right, and if we substitute back in there for our thermal stress, our thermal strain, that's going to be alpha times delta T times L, and put in our stress sigma over E times L, again equals 0. So we solve for sigma to get basically the thermally induced stress. And that's going to look something like this, where we have sigma is equal to the elastic modulus times minus alpha delta T. Right? And if our delta T is positive, then this is going to be compressive. Compressive stress for positive delta T. Right? Which kind of makes sense. If this thing heats up and it tries to push against the walls are going to push back and give it a compressive stress. So let's take a look at another example here. This example here has two different kinds of bars, right? Bar B, the two B bars are made of aluminum, and the bar in the middle, C, is made of stainless steel. We're given the cross-sectional area, we're given the temperature that this thing was at when it was first assembled, and we want to find the normal stresses in the bars after a 40 kip load is applied and the temperature is increased to 250 degrees. So this A member down at the bottom here says that it's rigid, which basically means that we can't have different deflections of the B bars and the C bars. So that means we can write something like this. We know that delta B has to be equal to delta C. Let me fix this funny line here again. Right, delta B has to be equal to delta C. We can also write that delta B is equal to the strain in B times the original length of B, which then is going to be equal to just a moment. Which then is going to be equal to alpha B delta B plus sigma B of the elastic modulus of B times LB. And we can write a similar expression for delta C. That's just going to be the strain in C times the length of C, and then expansion coefficient for C times delta T plus the stress in C, sigma C over EC times LC. All right, so let's continue. Basically what we want to know is the normal stresses in the bars. So we want to know sigma b right here, normal stresses in the bars. We want to know sigma b and sigma c. So we can write the following. If delta B is equal to delta C, then we can write alpha B delta T. Oh, why is it doing that? Alpha B delta T plus sigma B over E B times LB equals alpha C times delta T plus sigma C over elastic modulus of C times LC. However, this is two unknowns and only one equation. Right? We need another equation. In order to solve this, this for both sigma C and sigma B. So our two unknowns here, I should be clear about that. The unknowns are sigma B and sigma C. All right. So we need another equation. We can do a free body diagram of the rigid plate A. To draw what that looks like, we're going to have P coming down here. We're going to have FB moving up. We're going to have FC moving up. If we do the summation of our forces in the y direction there, we're going to have minus P plus FC plus 2FB. We can then rewrite that like 2 times sigma B times A, that's the cross-sectional area of that bar, plus sigma C times A equals P. So now we have two equations and two unknowns. Here's one equation. Here's our second equation. Right? We can solve for sigma B in this case. That's just going to look like 1 over 2A times P minus sigma C times A. And we can substitute that expression for sigma B back into equation 1. Let's go to a new page here. So we can substitute sorry about the mess here. We could substitute that back into equation 1. Alright, so that would look something like alpha B delta T plus 1 over EB (1 over 2A) P minus sigma C A LB. All of that is equal to alpha C times delta T plus sigma C over EC times LC. All right, and if we did the math, here to solve for sigma c, we would get something that looks like the following. So sigma c is equal to alpha b delta t L b minus alpha c delta t L c plus LB P over EB 2A. And then all of that over LC over EC. Again, that crazy line. Plus LB over 2EB. Then, if we go ahead and put in all of our values here, we can solve for this sigma c. So the value of alpha b, let's go back and look at what that was. This is the alpha for bar b. It's 12.5 times 10 to the minus 6th, basically strain per degrees Fahrenheit. So let's put that in there for alpha b. We've got 12.5 times 10 to the minus 6th, 1 over degrees Fahrenheit. Our delta T is going to be 250 minus 72 degrees Fahrenheit. Our original length here is 3 feet. And we have alpha C is the other thermal expansion coefficient, 9.6 times 10 to the minus 6th, 1 over degrees Fahrenheit, 250 minus 72 degrees Fahrenheit, times an original length of 6 feet. Then we also have this last term here, which is going to be 3 feet times 40,000 pounds over 10,600 times 10 to the third psi times 2 times 2 inches squared. So that 2 inches squared is the cross section, is the cross section of the bar. All of that over LC over EC, which is 6 feet over 28,000 times 10 to the third psi, plus 3 feet over 2 times 10,600 times 10 to the third psi. And you have to be a little bit careful here with how all of our things are going to cancel, right? We have to make sure that all of our units are going to cancel. And if we do a unit check, what we end up with is psi at the end here. So 2100, negative 2101 psi. That's also equal to negative 2.1 ksi, kilopounds per square inch. We could also call that 2.1 ksi in compression. Right. So any of those would be a legitimate answer for sigma c. All right, and to find sigma b and basically finish the problem, we just go back to the sigma b equation that we had earlier, 1 over 2a times P minus sigma CA, which in this case is over 2, and A is 2 square inches, and we've got actually, hold on a second. Let's rewrite that equation just once here. Let me erase that a bit. Let's replace this with 1 over 2 times P over A minus sigma C. So basically, I just multiplied through by that A. So I have 1/2, and then 40,000 pound force over 2 square inches minus a negative 2100 pound force per inch squared. That's the sigma C we came up with earlier. That's going to give us 11,050 psi, which is going to give us 11.05 ksi, or 11.05 ksi in tension. So there's our sigma B. So that solves our problem of what are the stresses. That's what we were after right here. Find the normal stresses in the bars after we put a 40 kip load on here for P and increase the temperature. So those are our answers. And let me know if you have any questions. Thank you.